Let us continue our exercises with now some exercises on piecewise defined functions, that is functions whose formulas look like this, which are different, that is the rule for the function itself is different in different parts of its domain. So in this next 4 exercises we have to draw the graphs of the given functions, which are each one of them is piecewise defined. So let us see this one. You can see that the domain of this function is the closed interval 0, 2 because our input x comes from there. So in the graph also we need to concentrate only on those values of x. So we don't need the negative x-axis. So we are drawing y-axis somewhat towards this side. Okay, let us first choose a scale and locate the points 1 and 2. Say this is 1 and this is 2. So accordingly on the y-axis also this is 1. Now in this part of the domain, in the closed interval 0, 1, the function is the identity function and we know what its graph is. Its graph is the straight line passing through the origin which makes 45-degree angle with the positive x-axis. So in this part this is the graph. And what about here? Note that here actually you cannot take x equal to 1, but just to figure out what the graph is, instead of taking x equal to 1, you can see one thing. You can immediately see that the nature of this formula f of x equal to 2 minus x tells us that the graph, whatever it is, it's going to be a straight line. But which straight line? This one, y equal to 2 minus x. Now although you cannot put x equal to 1 here in this function, but you can put x equal to 1 in this equation. Doing that, you see that when x is 1, then y is also 1. So that means the graph of this equation is the straight line that passes through the point 1, 1, and we need one more point. So you put x equal to 2, you get y equal to 0. So this is the other point through which also the straight line passes. So that means in this part the graph will be this. This line segment is not the graph of this equation because here there is no restriction on x, but it is the graph of this function which has been defined to be 2 minus x in this part of its domain. So this is the graph of our function f of x. In exercise 52, we have a function g of x, and that function is again just like f. This g also has domain 0, 2, closed interval 0, 2. Now in the first half, the formula is 1 minus x. And in the second half, the formula is 2 minus x. or to show things in full detail, we put 1 here, because on the y-axis this much is 1 and that is the same as the x-axis. Okay, so here also the function is having different formulas on this different parts of the domain. So in the first part, its formula is 1 minus x, whose graph is going to be a straight line again. But which straight line? If we put x equal to 0, we get y equal to 1. So that means this is a point, 0, 1 is a point on this graph. And if we put x equal to 1, we get y equal to 0. So this is another point on the graph. So in this part, the graph is this straight line. And in the second part, the definition is 2 minus x. If you put x equal to 2, you get x equal to, g of x equal to 0, y equal to 0. So 2, 0 is a point on this graph. Now you cannot put, of course, x equal to 1 here, but just to figure out what the straight line is, you can put x equal to 1 in this expression that gives you a value y equal to 1. So that means 1, 1 could have been a point on this graph, but it is not, because we cannot put x equal to 1 and use this formula. That is not allowed by the definition of the function. The definition says that when x is 1, you have to use this formula instead. So that means here have I taken the scale somewhat wrongly? No, it's okay. So because this point is not on the graph, so we enclose it within a very small circle and then draw the other half like this. This very small circle prevents this line from reaching this point, which expresses the fact that this point is not a part of the graph. So let us see once more what the points on the graph actually are. All the points on this straight line segment, including its endpoints, that is, this point is also a part of the graph, this point is also a part of the graph. Along with that, all the points on this straight line segment, including this endpoint but not this endpoint. Okay, so that is the graph of g of x. So you can see that unlike the graph of f of x, here the graph is broken into two disconnected pieces. This is not broken, but this is broken. In exercise 53, we have the function capital F of x. This is defined to be 3 minus x when x is less than or equal to 1 and 2x when x is greater than 1. So unlike the functions small f and small g, the domain of capital F is the entire real line. Here, although it seems like x is restricted, but only in the sense that it here in this part of the definition x cannot be greater than 1. X can take all the values less than or equal to 1, and in this part x is taking all the values strictly greater than 1. So that means combining these two things, actually all real numbers x are to be taken. So here the domain is the entire set of real numbers. And because now negative x values are also there, so we won't draw the graph like this. We will draw the y-axis in the middle. X 0 y. Let us take x, let us take this much as 1, 2, 3, 1, 2, 3. There will be a 4 here. We can understand the scale. Okay. Now to figure out what the graph is in this part, we put x equal to 1 first. Then putting x equal to, so this is 1. You get y equal to 2, or rather f of 1 is 2. So that means when our input is 1, the output is 2. So this is 1 point on the graph of this function capital F. To figure out what the graph will be in this part, let's put another point x, which is also less than or equal to 1. We can conveniently put x equal to 0. So when x is 0, the y value, the output value is 3. So that means this is another point on the graph. And from the nature of this equation, f of x equal to 3 minus x, we know that the graph is going to be a straight line. So we join these two. And we extend the straight line indefinitely on that side, because now our x value has no lower bound. We don't have any smallest x value like what we had there. There x can take the smallest value 0. Here however x can take any value. Any negative value also can be taken. So the graph extends like this on this side without any bound. What happens to the right of 1? Here the definition is 2x. Now we cannot put x equal to 1 of course in this function, but like before we can put x equal to 1 in this expression. When x is 1, then y is 2. So this should have been a point on the graph, but it is not. That is a different matter. Anyway, the straight line y equal to 2x passes through this point. To figure out another point, you put x equal to 2, then y will be equal to 4. So when x is 2, then y is 4. 1, 2, 3, 4. And you join these 2 points by a straight line. This straight line also is without any bound on this direction. So this is the graph of the function capital F. Here also, just like the graph of small f, the graph is not broken, and this is the point 1, 2. It's in one piece. And then another one, exercise 54. So here the function is capital G of x. Now in this case all the parts are not going to be straight lines, because here the definition is 1 over x when x is negative and x when x is non-negative. In this case also, the domain is the entire real line. So we draw y-axis in the middle. It is much more difficult to draw this graph, relatively more difficult than drawing straight line segments. And you know what this graph looks like. What the graph of y equal to 1 over x looks like when x is any non-zero real number. The graph looks like this. It's a graph in two disconnected pieces. On the positive side of the x-axis, the graph looks like this, and on the negative side it looks like this. So we will definitely have this here, because for negative x we are using this function in the definition of capital G, and for non-negative x we are just using the identity function. So let's first draw the easier part first. This we can draw much more easily. To draw this one, you can use the general shape of this. If you want, you can actually see in the solution you are supposed to draw the curve as nicely and as accurately as possible, which however is something that you should do. But here for this solution, it's enough for us to roughly draw a curve like this. You know how to draw the graph of this when x is negative. You just put negative values of x, calculate the corresponding values of y, plot those points and join those points as nicely as possible. What we normally do when we draw a graph of an equation. So this is the graph of g of x. It's also broken into two pieces like small g of x, two disconnected pieces. Okay, now after this, in exercise 55, we have to do the opposite. Here graphs are given, we have to find formulas for the corresponding functions. Find a formula for each function graph. Now two graphs will be given to us. In the text, one graph is drawn beside the other, but we cannot do that here because of lack of space, and there is no real need to do that anyway. So the first one is pretty easy. This is 1, this is 2. One comma 1. And what about the second one? The second one is more complicated than this. Oh, and this is A and this is B. For the second one, we need 4 points. One, two, three, 4. And on this side, we need 2 points. One, 2. So first of all, one, two, three, 4, 1 and 2. We have this point on the graph and we don't have this point on the graph. And this is a part of the graph. Just like that, this point is there in the graph, but this is not there. And this is another part of the graph. So this graph is broken. The next, so it goes like this, it falls down, then it goes up, and then again falls down. In this part, however, 4 is there. 4 is a point on the graph. Okay, so these are two given graphs. Now we need to figure out the functions whose graphs these are. Solution part A. In part A, you can see that this is just the graph of our function small f that we were given in exercise 51. So that means the function whose graph is this is just going to be that function which is what was given. It is x when x is non-negative and less than or equal to 1, and 2 minus x when x is greater than 1 and less than or equal to 2. So this graph corresponds to this piecewise defined function. But what about B? In B, you see that of course this also is the graph of some piecewise defined function, but the formula for that function will have 4 parts, and the domain of that function is the closed interval 0, 4. So we can say denote that function by anything actually. G, but don't confuse this G with that previous G of exercise 52. That is gone. First of all, when x lies between 0 and 1, where x is greater than or equal to 0 and strictly less than 1, then the value is constantly 2. So that means the function is 2 when x is greater than or equal to 0 and strictly less than 1. When x is 1, the functional value is 0 and it stays 0 until we reach 2. So when x is greater than or equal to 1 and less than 2, then the functional value is 0. Then when x is strictly greater than, or not strictly greater than 2, but in fact now when x is 2, then the functional value again has gone up to 2 to this level, and it stays as such until we reach x equal to 3. So that means again it is 2 when x is greater than or equal to 2 and less than 3, and when x is greater than or equal to 3 and less than or equal to 4, the value is 0. Now you can see that because the definitions of this function in these different parts actually match in some parts, so we can write the same function also like this: 2 when x belongs to the half open interval 0 comma 1, which corresponds to these inequalities, or that is union the half open interval 2 comma 3, and the functional value is 0 when x belongs to the half open interval 1 comma 2, with 1 included and 2 excluded, or when x belongs to the closed interval 3 comma 4. Okay, this is also the same function, like this one. Both of these expressions, they define the same function. Then there is another one like this. Find a formula for each function graphed. Again, graphs are given to us. I have arbitrarily taken one point without any measurement. Okay, so this is say some positive real number t, and this is half of t. This is t. Oh, so this is not t. This is 1. This distance is 1. It will be equal to t if t is also 1. That's how I have drawn it. I was thinking this is t comma t, but this is t comma 1. No harm in taking the scale like t is equal to 1. It can happen. So that's just it. This is one graph, and in part B, no, I won't be able to draw it here conveniently. Let's do it here instead. Here the x variable, the independent variable, is denoted by t rather than x, and there are 4 points, 1, 2, 3, 4. Using these 4 points, we are then drawing this is minus a, this is a, where a is some positive real number. Like that, t is also some positive real number. This is half of t, this is t, this is 3 times half of t, and this is 2t. These points 1, 2, 3, 4. Okay, so this is our second graph, and you can see from this graph which points are on the graph and which points are not on the graph. So this graph has 4 disconnected pieces. Solution. Okay, now in part A the graph is not broken, but it clearly will be the graph of a piecewise defined function which has 2 parts in its formula. So between 0 and t by 2, that is when x lies between 0 and t by 2, the functional value is 0. And when x lies between t by 2 and t, the graph is this. So in this, so that means we need the equation of this straight line. Now this straight line passes through these 2 points, and t comma 1. So the slope of this straight line will be what? 1 minus 0 divided by t minus t divided by 2, which is 2 divided by t. And because this straight line passes through t comma 1, so its equation will be this: y minus 1 equal to the slope times x minus t. Or because we want to use this formula to define the function, so we need y in terms of x. 1 plus 2x divided by t minus, if you we are performing the multiplication here, so 2x divided by t minus 2t divided by t, that means minus 2. So this becomes 2x divided by t minus 1. So you can write that when x is greater than t, and greater than t divided by 2 and less than or equal to t. You can verify by putting, say, x equal to t here. If you put x equal to t, then 2t divided by t is 2, 2 minus 1 is 1, so you get y equal to 1. And just for the sake of seeing what you have got is correct, you can put in this expression x equal to t over 2. If you do that, you get 1 minus 1, which is 0. That you cannot do in this function, but in the expression you can put. So what you get is not the functional value, but it's the y coordinate of the point on this line whose x coordinate is t divided by 2. So this is our first function. Now for the second function, we need space. Again, like before, when x lies between 0 and t by 2, t divided by 2, in the sense that x is greater than or equal to 0 but strictly less than t divided by 2, then the value is constantly a. Then when the value is here, that is when x is greater than or equal to t divided by 2 but strictly less than t, and the value is minus a, then it is again a when x is greater than or equal to t but strictly less than 3t divided by 2, and it is again minus a when x is, the last one is a closed interval, 2t. And like a previous similar situation, this can be written more compactly like this. The value is a when x belongs to either this half open interval 0 comma t divided by 2, or in this half open interval t comma 3t divided by 2, and it is minus a when x belongs to the half open interval t divided by 2 comma t, or here in this closed interval. Okay, so that is the solution to exercise 56. Then next we move to the greatest and least integer functions. The first exercise regarding this is exercise 57. For what values of x is, there are two parts. A, the greatest integer less than or equal to x is 0, and part B, the least integer greater than or equal to x is 0. We know that this happens if and only if x is less than 0. No, what am I saying? Not x is not less than 0, x is greater than or equal to 0 and strictly less than 1. If and only if that is if and only if x lies here, because only for such real numbers the greatest integer less than or equal to x is 0. If you find it difficult to understand, you just think of the points on the real line. 0, 1, you will have -1, and all the other real numbers in between, including these of course. So if your x lies here, it is greater than or equal to 0 but strictly less than 1, then your x is here somewhere. It can be 0 but it can never be 1. For such an x What are the integers that are less than or equal to x? All the non-positive integers. All the negative integers including 0. Among them the greatest one is 0. So that's why the greatest integer less than or equal to x, if your x is here, is 0. Among all these integers that are less than or equal to x, the greatest one is 0. But note that we cannot take x equal to 1, because the moment you touch x equal to 1, 1 itself becomes an integer less than or equal to x. So in that case, 0 will not be the greatest integer less than or equal to x. So that's why you cannot reach 1. You have to be strictly less than 1. Then like that, we know that the least integer greater than or equal to x is 0. If and only if you think like this, you have 0, you have 1, minus 1 and everything else. Now if so the least integer greater than or equal to x must be 0. So x itself cannot be greater than 0. So x has to be less than or equal to 0. But at the same time, x cannot be minus 1 or less than minus 1. It has to be strictly greater than minus 1, because now x will lie here. So for such an x, the integers that are greater than or equal to x are all the non-negative integers. Among them, the least one is 0. So that is the least integer greater than or equal to x. So that's why this is 0 if and only if this, that is if and only if x belongs to this half of an interval. What real numbers x satisfy the equation greatest integer less than or equal to x equal to least integer greater than or equal to x. Note that if x is an integer, if x belongs to the set of integers, then obviously these two are equal because both of them are equal to x. We now aim to show that the converse is also true. Namely, if this is true, then x has to be an integer. Now, assume that x is some real number for which this equation is true. Okay, now this is the greatest integer less than or equal to x. So that means this is less than or equal to x, and this is the least integer greater than or equal to x. So by the very definition of this, just like this one, x is less than or equal to this. Now you combine these inequalities with this, so you get now from this we get this. Actually, to conclude that x is an integer, either you can take either this or the second equality, that is enough. And how are we actually getting this conclusion from here? It's because we know that if x is not an integer, then this cannot be equal to x. This will be strictly less than x. So the fact that these two are equal forces us to conclude that x must be an integer. So the real numbers x that satisfy the equation are precisely the integers. Or you can view it like this also. The set of solutions of this equation is the set of integers. Does the least integer greater than or equal to minus x equal minus of the greatest integer less than or equal to x for all real x? Give reasons for your answer. The equation looks quite complicated if you use the definitions, but it turns out that actually this is always true. For every real number x, this is the case. So we now need to prove it. Let x be any real number. First of all, we use this. We know that the greatest integer less than or equal to x is of course less than or equal to x, but the next larger integer is strictly less than x. This cannot be equal to x because then this will lose its greatest nature. So the next one has to be strictly greater than x. Now this implies if we multiply throughout by -1, then we will get this. Minus x is less than or equal to minus greatest integer less than or equal to x. Now look at these inequalities. These inequalities tell us what? Specifically the second one. Actually, I think we don't need the first one. If we look at the second one, we see that minus x is a real number and minus of this is what? See, whatever this ultimately turns out to be, it's an integer. Positive, negative, we are not considering those things. The fact is that minus of this is itself an integer that is greater than or equal to minus x. And by definition, this is the least integer greater than or equal to minus x, whereas this is only some integer greater than or equal to minus x. So the least nature of this then gives us this, which is understandable. This is some integer greater than or equal to minus x, and among all such integers, this is the least. So this will be less than or equal to this one such integer. Also, so we have obtained this inequality. Now to prove that actually these two things are equal, we need the other inequality where you have the positions of these things switched. So for that, we start with the definition of this. This is the least integer greater than or equal to minus x. So that means this is an integer that is greater than or equal to minus x, and it's the least such integer. So that means if you take a smaller integer, in particular if you take the next smaller integer that can not be equal to x, that can also not be greater than that cannot be equal to minus x or greater than minus x. That has to be strictly less than minus x, because if this thing also becomes greater than or equal to minus x, then this cannot be the least integer greater than or equal to minus x, because this is already smaller than this. So that means this has to be strictly less than minus x. Okay, now again if we multiply throughout by -1, then we get what? Minus of this plus 1, because we are keeping the positions of these things intact, so the inequalities will get reversed. Minus of minus x is x, and this is greater than or equal to minus x. Okay, now if we use this part of these inequalities, then this second inequality tells us what? This is an integer less than or equal to x, and forget the minus sign here, only this one, the greatest integer value of this function at the point x, that by definition is the greatest integer less than or equal to x, whereas this is only some integer less than or equal to x. So the greatest nature of that will imply this. Okay, or now if you multiply again by -1 on both sides, then you get minus greatest integer value of x less than or equal to this least integer value of minus x. Now you combine these two inequalities, this one and this one. So this is greater than or equal to this, at the same time it is less than or equal to this, so that means they have to be equal. Thus note one more thing about this equation. X is any real number, so x itself can be negative also. Minus x does not mean that whatever you have here inside it has to be negative. You can take x equal to -1, still the equation will be true, or in fact you can take x equal to some negative real number that is not an integer, then also it will be true. So it is in general true. You can see that that equation is true in a very special case where x itself is an integer. When x is an integer, minus x is also an integer. So the left hand side of that equation is simply minus x. Whereas again, because x is an integer, this is x. So the right hand side is also minus x. But for fractional values of x also this is true, as we have shown. Okay, then next exercise 60. Graph the function f of x. This is again a partly defined function, but this time it involves those greatest integer and least integer function. why is f of x called the integer part of x? Let us first draw the graph. One half of the graph will be the graph of this and the other half will be the graph of this. The domain of the function f is the entire set of real numbers. Okay. Now, first of all, when x is 0, we have to use the greatest integer part of this definition. So then the value is also 0. So 0 comma 0 is a point on this graph. Now, when x stays positive, and stays positive means stays non-negative actually, because x equal to 0 is also a possibility, and is less than 1, then the greatest integer value is 0. So that means until we reach this point 1, if we start from here, the value of our function is constantly 0. Then once we reach 1, the value is 1. And then it stays 1 as we move from 1 to 2 until we reach 2. So that means this is a point on the graph. This is not a point on the graph. So here what we are doing is just we are drawing the graph of the greatest integer function, that's all. Just like that, when we reach the point 2, the value is 2 and it stays 2 as we move from 2 to 3 until we reach 3. So that means this is not a point on the graph, but this is a point on the graph. And it goes like that, like an infinite staircase on that side. What about the function on this side? Here we have to use the least integer function. So if you could have put x equal to 0 here, the value would have been 0. So if you just simply are drawing the graph of the least integer function, 0 comma 0 would be a point on that graph, which however is, we cannot say it's not a point on the graph, it's already a point on the graph, but that is coming from the greatest integer part, not the least integer part. Anyway, so now if we were moving from 0 to minus 1. Okay, then until you reach minus 1, that is, if your x is here somewhere, then what is the least integer greater than or equal to x? That is 0. The moment you reach minus 1, that value becomes minus 1. So that means here the graph is this. It does not reach the point minus 1. The moment it reaches minus 1, the value becomes minus 1, and as we move from minus 1 to minus 2, until we reach minus 2, the value stays constantly minus 1. So this is not a point on the graph, this is a point on the graph. Like that, when we move from minus 2 to minus 3, until we reach minus 3, the value is constantly minus 2. So on this side, the steps descend infinitely, without any bound. So here, near 0, the steps sort of they stop for a moment. If you continued drawing just the graph of the least integer function, the next one would have been here, and then the next one here, and so on. Similarly, if you extend the graph of the greatest integer function on this side, then the next one will be here and then here. But because of the partly defined nature or piecewise defined nature of our function f, it goes like this. It comes up, then stops for a moment, and then again it continues to ascend. So this is our graph. Now the second part of this exercise asks us to say why this function is called the integer part of x. I will not answer this part. I will give you a hint and leave it to you. The hint is just this. Say you take some value of x. Say x equal to 1. Okay. Let us start with the easier ones, that is the positive part. If you take x equal to 1, a value which is itself an integer, then first of all you will use the upper part of the definition, that means the greatest integer function. So your f of x will be 1 itself. So it's understandable that when your x is 1, the function also is giving you 1. So the integer part of the real number x equal to 1 is 1 itself. There is no fractional part. Okay. If you take a non-integral value, say for example 1.213, now this value is strictly greater than 1 and strictly less than 2. So its greatest integer value is 1. So that means f of 1.213 is 1. So in the real number 1.213, the integer part is 1. The fractional part is 0.213. And you can see that the same will be true if you take other values of x, any positive value. What happens when you take a value in between 0 and 1? say you calculate 0.21. By the definition of this function, it's the greatest integer value of 0.21, which is 0. So for this value also you can see that you are getting the integer part 0. Now we come to the negative side. Suppose you have minus 0.21. This time, because x is negative, you have to use the least integer part of the definition of f. So that means minus 0.21 is here somewhere, and here the value is 0. So you are again getting the integer part, which is 0. If you take an integer, of course you will get the integer only. Does not matter whether x is positive or negative, and correspondingly whether we are using the greatest integer or the least integer part of this definition. Our answer is going to be x. So that's not the interesting thing. The interesting thing occurs when you take a negative fractional value. Now what does the graph tell you here? Minus 1.21 is here somewhere between minus 2 and minus 1. Here the value of the function is minus 1. So that means this is minus 1. So you see that in this case again you are getting the integer part. Integer part is of a real number, is what you, after writing the real number in decimal system, whatever you have after decimal, you just don't think of that part. You think of what you have before decimal. That is the integer part. So that's why this function gives you the integer part of any real number. You have to write these observations in a general fashion, taking into account all possibilities. That's what you have to do in the second part of this solution. Okay, next, some exercises on even and odd functions. Assume that f is an even function. G is an odd function. And both f and g are defined on the entire real line. So that means both of them have the set of entire set of real numbers as their domain. Which of the following were defined, that is, we are now going to give some functions. Which of these functions are even and which are odd? Part A, the product of f and g. Part B, the quotient f divided by g. Part C, the quotient g divided by f. Part D, the product of f with itself, that is f square. Part E, g square. Part F, the composition f composition g. Part G, the composition g composition f. Part H, the composition f composition f, and I, g composition g. Okay, because the domains of both the functions are given to be R, so we don't have to think about their domains too much. The only thing is that we have to take care of the domain of this function in these two cases. In the other cases it's very easy. That is because the domains of these two functions are not the entire real line. In part A, the domain of fg is R, because it needs to be the intersection of the domains of f and g in order for us to be able to have the input x, in both the domains of f and g. Now in this case, since both the domains are equal to R, so the intersection is also R. For any x belonging to R, minus x also belongs to R. That is something we need to mention when we are going to verify whether the function in question is even or odd. But since that is obviously true, so we are not going to say that here. For any x belonging to R, we just simply write fg minus x. We need to say, in general we need to say that minus x also belongs to the domain, because otherwise this would not make sense. By definition, this is f of minus x times g of minus x, because f is given to be even and g is given to be odd. So f of minus x is f of x and g of minus x is minus g of x. So if G is odd, okay, B is given to be F divided by G. The domain of F divided by G is this set of all real numbers such that G of X is not equal to 0. For simplicity, let us give it a name also. Let us call this A. Now, because here A is not the entire set of real numbers, we need to make sure that whenever we are choosing an input X from A, its negative minus X also belongs to A. Let X belong to A, then G of X is not equal to 0, since G of minus X, because it's given that G is an odd function, so G of minus X is minus G of X. We have G of minus X also not equal to 0, and so minus X also belongs to A. Okay, so now it makes sense to ask whether F by G is even or odd. Now for any X belonging to A, now we know that minus X is also in A, so we can calculate the value of the function at minus X, value of F divided by G. By the definition of quotient of two functions, this is F of minus X divided by G of minus X. F is even, so the numerator is F of X. G is odd, the denominator is minus G of X. So this is odd. This is part B. Part C is similar. You just switch F and G, and because of the similarity you can see that G divided by F will also be odd. There is, however, one difference, that here the function in the numerator is odd and the one in the denominator is even. That will not affect this part. So looking at the solution of part B, you can see that part C also has an exactly similar solution. So this I leave to you. And the answer is simply this. Just like part B, this is an odd function, you will see. Then D. Here again things are easy as far as domain is concerned. The domain of f square is the entire set of real numbers. For any x belonging to R, we have f square minus x is f of minus x times f of minus x, because f is given to be even, so it's again f of x times f of x. So f square is even and part E is similar, so this one also you do. And despite G being odd, this type of calculation will give you what? If you have G in place of F, after this step you will get minus of Gx times minus of Gx, that is going to give you again Gx times Gx. So G square will be even. Part F. The domain of F composition G is, we know from the definition of composition and from the things we saw previously about compositions, the domain is the same as the domain of G, which is R. F of G of minus x. F of, because G is odd, minus of Gx. But F is even, so this is F of G of x. So F composition G is even. Part G. The domain of G composition F is the domain of F, which is R. Minus x is equal to G of f of minus x. So here minus vanishes now itself, because f is even. So G composition F is also even. The domain of F composition F is R for any real number x this is equal to f of minus x. Because f is even, f of minus x is f of x. So F composition F is even. Note carefully that F square is not the same as F composition F. F square is the function obtained by multiplying F with itself, whereas this is the function obtained by composing F with itself. Composition and multiplication are two entirely different things. And finally I. This is R for any x belonging to R. Okay, this time we will not be able to get rid of the minus sign because we don't have any even function, and also we are dealing with composition. So the minus sign will not be taken care of by square, the thing that we had here. In spite of having g an odd function, g square turned out to be an even function. Here however, g composition g will not be even, it will be odd, which again shows in a different manner that g square is different from g composition g. G square is even and g composition g is odd. And the nature, the reason for the oddness is this. First of all, because g is odd, this is minus of g of x. Again, because g is odd, the minus comes outside. So this is odd. Can a function be both even and odd at the same time? Give reasons for your answer. Let D be a subset of the set of real numbers with the property that whenever x is, or I should be more specific about this, D be a non-empty subset, because I want to use D, I want to make D the domain of some function. So we need non-emptiness with the property that x belongs to D implies minus x belongs to D. Let f be a function from D into R, that is, f is a real valued function whose domain is D. And such that f is both even and odd. Then let us see what happens. Then for any point in the domain, okay, what is f of minus x? On the one hand, this is going to be minus of f of x because f is odd. On the other hand, this is also going to be f of x because f is also even. This implies 2 times f of x, equating minus of f of x and f of x, we get 2 times f of x equal to 0 or f of x equal to 0. So the only function with D as domain that is simultaneously even and odd is the function that is constantly 0 on D. Is the function that is constantly 0 on D, that is f of x is equal to 0 for all x belonging to D. Okay, it has to be constant and that constant has to be 0. That is the only case in which it can be even as well as odd. And then finally there are 2 graphing exercises which of course has to be solved using a graphing calculator or some sort of graphing device. Let's just see the exercises. I am not going to solve it here for obvious reasons. Exercise 63, this is continuation of example 5. You go to example 5 and you will understand why it's a continuation. Graph the functions f of x equal to square root of x and g of x equal to square root of 1 minus x. Together with their a sum, b product, c the two differences f minus g and g minus f, and d the two quotients. And there is another one, another similar one. I need ink. Let f of x be the function x minus 7 and g of x be the square function x square. Graph f and g together with f composition g and g composition f. If you don't have a graphing calculator, you can, like I don't have a graphing calculator, you can search on the net this. Desmos graphing calculator. You search this in your Chrome or whatever web browser you are using. You will see that you get an online graphing facility. There you can do all these things, and there you just you go to that website, the first search result. There you just have to put the formulas for these functions and the site will automatically generate the graph for you. You can simultaneously graph many functions, okay, in that same graphing window. What more is the fact that you see here we cannot put negative values of x. So those things are automatically figured out by the program itself in that website. You don't have to additionally input the natural domains. You just use the formulas, you will get the graphs. So that is perfect for this type of exercises. So with this, the current set of exercises is over. After this, we will go to the next section, which involves shifting graphs. That is, if one changes an equation slightly in a particular manner, the graph of the new equation is actually nothing but the graph of the old equation shifted in some manner. We will see those things in the next calculus video. And the next video is, today is 21st, 22nd, 23rd. The next one is on 24th. And it's on number theory. Okay, so see you in the next video. If you want to say something about these things, you can comment in the comment section below. So until then, until the next time, this is me, Lucifer, from a mathematical room. Have a nice night.